talk about some topology here. So the first definition is the open set. In the matrix space here, we define the open board in the following way. So we have the reference point A here, and all the point around it, like within this distance epsilon, then we call it an open ball. So in the graph, it looks like this one. So in the matrix space, we have a reference point A, and we have the distance epsilon larger than 0, and the open ball looks like this one, just a ball, right? So for any point within this open ball, I can write it down there. You can see that the distance between these two, for example, like x, d of x and a, should smaller than epsilon here, and that's we define the epsilon open ball around. Use the round symbol here. Okay, should be x, and this is a, to be consistent, right? So for all the point around x, the distance should be less than epsilon here. And of course, to define this ball, you have to have the reference point first, x, and the distance first. Okay. Right. Then the next definitions. A point in the set, a point small x in the set A here is said it is interior to 8 if there is a epsilon such that you can open the ball over there, and the whole ball will be fall within that set A. So what does it look like? Let's say that the set A look like this one, and we pick up a point that says that here, x. Okay, what is the definition say? What does the definition say? It says that there exists an epsilon larger than 0, and we can open open ball that is going to be contained within this set. So is there an epsilon? Yes, actually there's more than one possibility of epsilon. You can pick an epsilon that is small enough that is going to have an open ball within this set, and we are going to say that this point x is interior to the set A here. Okay, but what if we pick a point here? Let's say x plane. Is there any epsilon that is going to be allows you to open an open ball that is going to be contained in A? No. Yeah. So be careful when you want to examine whether that point is interior in the set. And we called all the interior point of this A as we use this symbol. Yeah, that means all point that is interior in A. And a set A is said to be open if for all elements or for all points in the set A is interior to A. Okay, that is this one. Okay, so for example, I use this open ball as the set A here, and this is an open set. Why is that? Because no matter which point you pick within this set A, let's say that x1 here, you can pick up the distance, which is this. We already know the it should, how to say it, the radius should be epsilon, right? And this will be distance between x star and the point you pick up x, right? And this will be epsilon minus d x1, and let me call it epsilon 1. And you just open another ball by using this distance, and it's going to guarantee that, I shoot the red one, epsilon 1. So this ball is going to be contained within the original open ball, right? So this is an open set. And you can do it, because when you try to verify it, you are going to say that for all x within the set A is going to be satisfied. Okay. For now, I just randomly pick up x1 to show you that works. And to prove it, you have to use for any points within that set. Okay. Right? Okay, and like for the question 5, I think it's quite intuitive. All of them are actually open. You can verify by yourself. The first case I just show you here. Okay, so I'm going to skip it. Then is the closed set. Okay, so this one is a little bit tricky. So a set B in the metric space is said to be closed if the complement of it is open. Okay, so actually we want to verify whether the complement of that set is open to determine whether that set is closed. So yeah, it's kind of a twist over there. Okay. And then is the counter set. So this is a kind of interesting set here. So this is how it constructs. Okay, so this is how the counter set is going to be constructed. So we can only focus on 0, 1, the interval in the 0, 1 here. So this is the first C0. Okay, then we are going to divide it into 3 pieces. Okay, and take the middle part